Now that we've seen a few questions where we apply stretches to a graph, let's look at one where we're just given the equation. In class example 1.33, we'll work with an absolute value function that is both reflected and stretched. So the function f of x, which is equal to the absolute value of x minus 5 plus 8, has a range of y greater than or equal to 8. This would make sense if we picture an absolute value function, typically with a vertex on 0, 0. The x minus 5 shows that we've shifted 5 to the right, having no effect on the range, but then moving 8 up means that our range would be greater than or equal to 8 rather than 0. So to obtain a function g of x, we reflect the graph y equals f of x about the line y equals 0. The line y equals 0 is another name for the x-axis. So this is a vertical reflection. And then we apply a vertical stretch by a factor of 1/4, meaning each y-coordinate is multiplied by 1/4. Note, when we talk about vertical stretch factors in a word problem, what it tells you is in fact the stretch factor. So even if this were talking about a horizontal stretch factor of 1/4, it would actually be a stretch factor of 1/4. We don't worry about the reciprocal until we go to work with the equation and having to write the coefficient there. So the first part asks us to determine an equation for y equals g of x in terms of f of x, and then in terms of x. What does it mean to write an equation in terms of f of x? It means that we simply represent the original function as f of x and represent the transformed function g of x as a transformed f of x, which is, say, we just write in the parameters that affect it. So here we had a reflection in the x-axis. That is a negative a value. And we had a vertical stretch by a factor of 1/4. That is an a value of 1/4. So our g of x equation would be negative 1/4 times f of x. If we then want to write that in terms of x, we would replace f of x with its original expression of absolute value x minus 5 plus 8. Notice that it is bracketed there. So those vertical lines are the absolute value brackets, and then we have rounded brackets around that. Using the distributive property, we will multiply that negative 1/4 to the absolute value brackets and also to the positive 8, generating a negative 2. A reminder, because it's been a while since you've worked with absolute value functions maybe, that the fact that there's an x minus 5 affected by an absolute value does not mean we'll change that to x plus 5. Right? It's only after that internal expression of x minus 5 is evaluated that we apply the absolute value function. Now, part B asks us to state the range of g of x. Well, remember our original range was y is greater than or equal to 8. So what happens if we reflect that over the x-axis? Well, if you can picture the original graph as being the blue one shown there, then the transform graph would be the green one, the one that is below the x-axis. Notice that the vertex of the original was at 5 and 8, and the new one is at 5 and negative 8. So instead of our range being above positive 8, we are below negative 8. It's important that you change both the direction of the inequality, but also that you change it from being positive 8 to negative 8. Now after that, we apply a vertical stretch of 1/4, which effectively shrinks our negative 8 to a negative 2. So this is what the original graph would look like compared to its transformed graph.